Good afternoon. I'm David Hahn, the Craig M. Burge Dean of the College of Engineering, and I'd like to welcome everyone to the first installment of our new speaker series. The goal of these lectures are to share the research successes of this college with our alumni and faculty and friends. Our first lecture is today, our inaugural series is around hypersonics. Hypersonics has been a large part of our college's strategic vision, and I'm really happy and excited today to share with you two of my colleagues' thoughts on hypersonics and answer your questions. I'll give a little bit of background. The speed of sound is about 760 miles per hour, or for some of you like myself that came up in the metric system, 340 meters per second. So we consider the speed of sound to be Mach 1. And that's named after Austrian physicist and philosopher Ernst Mach. So a typical bullet is about 1,700 miles per hour, more than 2+ times the speed of sound, so we call that Mach 2. And some of you remember the Concorde, which first flew in 1969. It traveled at twice the speed of sound. Its official Mach number was Mach 2.04. It could fly from London to New York in less than 3 hours, arriving before you left. Now, when we talk about hypersonics, which will be the focus of today, we're talking many times the speed of sound, typically 5 to 10 times the speed of sound, but it could be up to 20 times the speed of sound. So, imagine that trip from London to New York in 30 minutes. That would be something traveling at Mach 10. So what I'd like to do is to introduce my colleagues and our panelists today, Professors Erica Corral and Jesse Little. And I think they'll join us in a second with their videos. So Dr. Erica Corral earned her Bachelor of Science degree from University of Texas, El Paso, and then her PhD from Rice University, both in material science and engineering. She spent 3 years at Sandia National Labs, one of the premier Department of Energy laboratories, before joining us in 2008. She's been named a University of Arizona Distinguished Scholar in 2016, and her expertise is around materials and high temperature materials. My other colleague I'd like to introduce is Professor Dr. Jesse Little. He earned his PhD from The Ohio State University in 2010 and joined University of Arizona shortly thereafter. He's an Associate Fellow of AIAA and is currently the Associate Department Head of Aerospace and Mechanical Engineering here. His expertise is in the experimental study of the physics of flow and control of flow, particularly in high temperature flows. So we have a number of questions that our audience pre-submitted that I've pulled from, and I will also pull from the comment box or the Q&A today as you've submitted in real time. So I'd like to get started first by giving our first questions to my panelists. I guess I'll give Erica and Jesse just one opportunity to say any quick words before we get started. Erica, would you like to just say a welcome, and then Jesse?
Yeah, sure. Thank you, Dean Hahn. I'm looking forward to sharing some of the exciting activities going on at U of A, and look for and virtually connecting with former students that happen to be calling in, because all of this could not be done without their hard work and dedication to their education and training.
Thank you, Erica. Jesse?
I'm just happy to be here. We've got a lot of exciting things going on in hypersonics, both in the College of Engineering and the university at large. We're excited to share those with you today.
Excellent, thank you. So the first question, I'll go to Erica and then give Jesse the same opportunity to answer this one, just speaking to Erica's comment about our students. So looking at our educational mission, we're going to talk a lot about research, but let's talk about education for a moment. Now, how might educational institutions such as ours keep pace and prepare students for hypersonic work once they leave the university to support commercial flight or defense sectors? What are your views on that, Erica?
I think we're in a unique position to train a skill set and academic background that focuses on all aspects of the technology that are necessary in order to sustain a high-speed flight system. So there's a range of basic disciplines across physical sciences and engineering that really come together, but a university is unique to be able to provide that cross-disciplinary training and education foundation.
Jesse?
Yeah, I mean, I think we have a specific focus here that we can offer a lot of interesting hands-on applications to. Part of this is obviously learning the fundamentals in coursework, but we have some very capable facilities, and we're going to be able to give students hands-on perspective into many of these problems, both in the lab and also virtually. So we want to be able to do that virtually and in person, because we have different kinds of students who want to know more about hypersonics, from the traditional student to the continuing education student who might be in the workforce for a while.
Excellent. So good. So I wanted to, our audience to kind of touch on the educational aspects of what we do, but now we're really going to turn to, I think, why many of you joined us, to hear a little bit about our Hypersonics program and then move into many technical questions. So we're going to start this with a brief presentation, a slideshow by Erica and Jesse. They're going to tag team that essentially. So I'm going to turn now over to Eric and Jesse to pull up their slides and share their screen and let them bring us through their presentation.
Okay. Well, I wanted to thank everybody who organized this webinar, to invite Jesse and I to share with you some of the work and activities going on in hypersonics. Our contact information is here, and you can reach out to us at any time. The key challenges for achieving hypersonic flight are really hot. And I say that not because it's like 110 degrees right now in Tucson, but because if you look at different aspects of a high-speed flight vehicle system and the technology required to sustain that flight, they are everywhere from a commercial airliner application, which is a rendition of the Boeing commercial airliner that would be able to take passengers from New York to London in less than 2 hours, flying at a speed called Mach 5, which is around 4,000 miles per hour. Hypersonic flight is sustained flight above this Mach number 5, and most of the high-speed flight systems that we'll be talking about in the technology development area that is being pursued in basic and applied research programs are dedicated to this flight speed above Mach 5. And so some launch vehicles that you're familiar with, or space shuttle vehicles that you're familiar with, achieve a sustained flight above Mach 5. Propulsion systems and how we operate and maneuver these systems are also part of this technology overview that will impact not only DoD type applications, but also energy applications where materials and systems have to operate at these very extreme conditions.
Yeah, so one of the main issues is this interdisciplinary challenge we had in hypersonic flight. And this is really a top national priority. You can see some quotes from Michael Griffin, the former Undersecretary of Defense. He's since moved on, but hypersonic remains a very big focus in the DoD. We have some key challenges here associated with materials and structures, coming back to the issue of heating that Erica mentioned. Also GNC, guidance, navigation, and control. How do you navigate these things around? These are maneuverable. They're not sort of like ballistic trajectories where you just shoot them up and hope they come down the right location. They're highly maneuverable systems, so that's a challenge. The hypersonic environment is a challenge, as you can see from these pictures, that all these nice glowing plasmas. Aerodynamics and propulsion are a challenge in all sorts of aerodynamic applications, and especially so in hypersonics. And one that's really gained a lot of attention is the national and Arizona workforce. Arizona, obviously, for us, we have a lot of aero and even hypersonic activities going on in the state. But this is a national concern, that the workforce that was doing a lot of this work during the Cold War is aging, and we need an influx of young, talented people. So that's been a priority of the DoD. You can see a couple examples of hypersonic vehicles here at the bottom. All the way down to Mach 5, that's where we would say the lowest hypersonic Mach number, and all the way up to Mach 25, and everywhere in between. So the low Mach number stuff is typically an air breathing system. It has an engine. These are sometimes called hypersonic cruise missiles or cruise vehicles. This would also most likely be how a commercial hypersonic vehicle would be powered. Next, we come up to the higher Mach numbers in the boost glide. These are vehicles that are boosted up to altitude and then glide back down with highly maneuverable control surfaces. And then finally, everyone I think probably is familiar with the space shuttle and in this case, re-entry capsule and all the challenges associated with re-entry in that case.
So at the University of Arizona, under the College of Engineering leadership, we formed a Arizona Research Center for Hypersonics. And this slide covers the aspects of the vehicle technology and where the subject matter expertise comes in from a group of faculty at the University of Arizona that have been working together on bridging these interdisciplinary research gaps to address a system solution or approach to finding system solutions. In materials, structure, and thermal protection systems, it is the part of the vehicle that is responsible for the aerodynamic shape, so the sharp leading edges. Those materials are going to be interacting with the gas species on the surfaces and getting extremely hot versus the body and acreage area of the vehicles. So materials are in the entire system, from propulsion to thermal protection to guidance and environment effects. So the work that we're doing here is at the University of Arizona is cutting edge in the sharp leading edge material aspect, additive manufacturing, simulation, and theory that can be applied to the whole system of materials across the vehicle. Hypersonic environment is the unique phenomenon that happens when a vehicle is in a medium at a given altitude and interacting with the gas species at very high flight velocities. Those extreme phenomenon are special to a hypersonic vehicle, and we're applying our expertise in land-based observation of the stars to help us understand what kind of signatures are happening in space and for hypersonic. GNC, guidance, navigation, and control. The vehicle needs to see where it's going and keep that trajectory. So a lot of the new challenges in hypersonics for GNC are new opportunities for research that cross disciplines with the faculty here. In propulsion, there's different ways that the vehicle can be powered, and those create different requirements for technology that needs to be developed in order to sustain that propulsion system. And in the aerodynamics area, our aerospace and mechanical engineering department has had the longest legacy of active faculty doing research in this area that go from aerodynamics and into new faculty hires that are in aerothermodynamics that cover some of the non-equilibrium gas flow interactions that happen at these extremely high Mach numbers, in addition to standing up facilities that can provide students opportunities to do hands-on learning in these high-speed flight environments. So with this set of exceptional faculty that have been doing this for a long time, we're also creating a new Masters of Engineering program in hypersonics, where we'll be taking on a novel approach or a novel approach for the country to help assess this workforce development and readiness, where we will not only be able to train students in the research lab, but also in the classroom, where we'll have faculty doing co-teaching in their subject matter expertise as applied to a system for materials, propulsion, aero, GNC, and environment.
Yeah, so this graph shows some of the investments both that they made internally by the university and also from our external sponsors. The university has invested in infrastructure in our high temperature testing lab that's directed by Erica, as well as some high-speed wind tunnels that I'll speak about a little bit later. We've also hired 5 new faculty in the MSc and AME departments who are doing hypersonic related work. You can see a breakdown of funding here on the left. This is since 2011. In total, it's about $13.5 million, and that's just a little bit of FY21. So there's quite a bit more coming in FY21 that's been announced that hasn't hit the books yet. Our main sponsor here is the Air Force Office of Scientific Research. This is the basic research arm of the Air Force, followed by the Navy, who's really invested a lot in recent years in hypersonics. And you can see the other players down the line, like Raytheon, National Science Foundation, et cetera. You can also see it right, the running total. You can see that we've got a very nice trajectory. We're adding projects, funding each year, so we are certainly not slowing down here. And we're really ramping up with our new hires and the national interest in hypersonics. So we're really well positioned here as a national player. So this leads into some of our facilities. I'm going to speak a little bit about wind tunnels, and then we'll turn it over to Erica on the high temperature facilities. So this is a graph compiled by my colleague Alex Craig, who spent a lot of time on this, of Mach number against sort of scale and cost. So Mach numbers at the left, you can see Mach 4 going up to Mach 8 and even beyond potentially. And on the x-axis is basic research on the left and T&E on the right. So when I say T&E, this is test and evaluation. So test and evaluation is typically things that are done by big government labs. These are prototypes, those types of things that industry or different government research labs would be testing. And on the left is where universities typically lie. Small facilities, limited in size, very fundamental work, nothing that looks like a vehicle. And what we've done at the University of Arizona is we've been able to sort of bridge this gap and carve out a space in between, that we can take our fundamental understanding, our basic research knowledge, our skills that we've developed over the many years of fundamental research here at U of A, and apply those to hypersonics in more applied systems, because we have the facilities to allow us to do that at a larger scale. We specifically carved out a niche around Mach 5. You can see two facilities there at Mach 5 right in the middle of your screen next to the Arizona logo. One is a specialized quiet Mach number facility. It's called a Ludwig tube that's very accurately simulates the atmosphere in flight. And the other is a longer duration facility that's much more flexible in terms of simulating both external flows and internal flows. And I'll speak about those next. Okay, so this is the first facility. This is the Arizona Supersonic wind tunnel, and it's supersonic right now because it's capped out at Mach 4. We are actively planning and to move this thing up to Mach 5 and potentially beyond. It turns out there's still a lot of very interesting hypersonics relevant physics that happen at Mach 4 and even below. It's a fairly large scale facility. In fact, it's the largest facility of its type at a U.S. institution. It's a 15-inch by 15-inch test section. That's where the work goes on. And you can see that a picture of it there at the left to get a kind of an idea of the scale. There's a planform view also at the left, looking down. If anybody of you are familiar with the A&E building, you might recognize some of those rooms. And what I want to point your attention to is that figure in the middle that shows something that's notionally a vehicle. Would be some sort of inlet for an air-breathing engine of some kind on the right. And on the left, a highly resolved image of the flow field. So what we really want to be able to do is to take our basic research skills and apply it and put these against some applied systems to really fill a national need. It allows us to really have a foot in both worlds, and it prepares both our students and all the research staff involved to really project into what's going on at a highly relevant level with DoD and DoD contractors. And the other facility that I'll mention for a wind tunnel facility, this is directed by Professor Alex Craig. It goes by Stewart. You can see his contact information there at the bottom right. This is a Mach 5 Ludwig tube. This is specifically Mach 5, and it's a specialized facility that allows accurate simulation of the atmosphere. So this facility design's a little bit different. It's 15 inches in diameter. It's not a square cross section. It's a circular cross section. There are other unique features that Alex, I'm sure, would love to tell you about this facility that allow it to better simulate the flight environment. And this really complements the other facility that I showed you. One is short duration, very accurately simulates the flight environment, which is this one, and Mach 5 Ludwig tube. The other one is a long duration facility that allows us to simulate both the external and the internal flow paths. So these are two unique facilities that really set us apart among U.S. institutions. These are there are no other universities that can offer the same kind of capabilities under one roof. And one thing that I didn't mention that I want to say now in transitioning over to Erica's facilities is these are cold tunnels, as we call them. So they do not simulate the heating effects that you get in hypersonics. There's a lot of good physics that we can get our hands around at Mach 5 when things are cold. And there's really a niche we've carved out at Mach 5 because of some of the interest in that lower Mach number range, which I'd be happy to speak to people about that offline. But really the heating is what starts to matter when we start to take a full look at the full picture here. And that's where Erica's facilities come into play, which if you want to give a comparative number, this facility that I'm showing here is about Erica's facility has about 100 times greater enthalpy than this facility I'm showing here.
Thanks, Jesse. So in order to see how the materials are going to behave in the extreme hypersonic flight environment and at the sharp leading edges where, because of aerodynamic heating, the surfaces that are sharp generate heat quicker, faster, and to higher heat load. And so the materials that we're developing are for use at above Mach 20. And at that Mach number, you're going to have extreme aerothermal heating on the surface of the solid. So what we've been developing in our lab is an approach to evaluate and screen materials response under extreme heat loads. And so our most important screening method is this torch. It is a oxyacetylene torch that delivers a heat load to the surface of the sample that's shown here in the center. It's a disc of a high temperature ceramic, ultra high temperature ceramic, being held in compression by some alumina ceramic rods. And the material is reacting with the gas species hitting the surface. And those beautiful particles that you see kind of like decorating like confetti are actually refractory ceramic particles that we dropped over the experiment in order to calculate the velocity of the incoming gas onto the surface so that we could develop kinetic-based reaction models for how the material behaves. And Professor Little was actually very helpful in helping us determine whether or not we should do a particle tracking velocimetry experiment or a different type of experiment to get the information we needed from the flow interacting to the solid. So this is a gorgeous picture, and we have a lot of students to thank over the years who have developed this facility with us. So on the material side, when we make them, we have to create the material to provide the response in application that we desire. So in order to do that, we have to work with materials that are very difficult to consolidate, densify, and turn into a solid part. So we have a research facility that not only does materials manufacturing and research, but we can also do the testing. And so the facility on the left is very, very unique in the country in that we can manufacture large scale, ultra high temperature ceramics using a direct current heating method that basically develops joule heating around the samples and elevates their temperature rapidly. So we can create heat profiles that maximize thermodynamics and kinetics of formation of the solid. And with that, we can create materials for application in hypersonics that go into propulsion systems or on antenna covers that are called radomes for certain applications, and on thermal protection system materials. So we use the materials to gain optical, electrical, mechanical, and thermal response properties that we desire in this application. So with that is a brief introduction to some of the activities going on at U of A, and we all welcome your questions. And I want to highlight our website that's hosted in the College of Engineering that lists all the faculty doing research in this area, where you can reach out to any of us and get more information about the activities going on here. Thank you.
Thank you, Erica and Jesse, for the presentation. You can stop sharing the screen and take us back to the panel discussion, and we'll move into our Q&A. So let's just step back a little bit and set the stage. I'll go to you, Erica, first, and then Jesse. You know, what drew you to this very exciting area, and how did your training help, and how did you end up at the University of Arizona?
I was interested in pursuing research in hypersonics because of all of the challenges that were really exciting from a materials standpoint that go into this extremely hostile environment for the solid of the surface. So that to me was very exciting. And the University of Arizona was the perfect place to stand up this research program, and has been a outstanding supporter of this program over the years. And one of the unique aspects of U of A is that we're the only institution of higher learning in the state of Arizona that offers baccalaureate and post-baccalaureate degrees in materials engineering that's certified by our ABET accreditation board. So we can train students to become professional engineers in materials and engineering, unique to Arizona, but also to the Southwest. There's only one institution in New Mexico, three in Texas that serve this region to train students in materials engineering. So for that reason, U of A was a perfect fit.
Jesse?
I mean, for me, the Aerospace Mechanical Engineering Department at University of Arizona has a very long history of impactful faculty in the area of general aerodynamics and fluid dynamics. So, coming up as a student, seeing how many papers came out of the University of Arizona and the fantastic work that's being done has been done by colleagues, what I now call colleagues here at U of A, really drew me here. I mean, this is a international destination for high impact research in aerodynamics and fluid dynamics.
Excellent. Thank you very much. So for you, Erica, as you noted in your talk, hypersonic vehicles really require special materials to maintain that integrity. Can you just give a little insight into what specific materials you're looking at?
Yes, we work with a class of materials that are called ultra-high temperature ceramics. They're refractory solids that are mostly composed of carbides, nitrides, and boride systems. And they have a melting temperature that is equivalent to 1/3 the surface temperature of the sun. So they don't melt until above 3,000 C. And that by itself elevates them to a category of materials selection that are going to be the ones that can stand up to this extreme heating environment.
Yeah, wow, those are great. Jesse, you do a lot of experimental wind tunnel testing with scale models. Do you have any plans to scale up your test and maybe work with private companies or DoD research arms to move to some actual flight tests at some time with your technologies?
Yeah, this is actually an exciting part of what's going on in hypersonics today. I mean, some years ago, as a student or even a faculty member, your opportunities to get involved with flight testing were minimal, if at all. And there's actually been a push now because of the national interest in hypersonics to have opportunities for universities to get on flight tests. So we're actually starting up a new project now with some colleagues in my department where we'll be involved in a flight test that's occurring out of DLR, which is essentially the German version of NASA. There are also other opportunities that the DoD has universities on that are now flying or plan to be flying. We have faculty working on many of these, and there are others in the pipeline. There are a couple new. There's a new X-plane that's going to be open to flight test work that will have modules for specifically university or small business type testing. And there's also some private companies who are building these reusable flight test systems. So, this is something that's really advanced in the last 5 years or so. And, prior to this, there really weren't opportunities like this for universities to be involved. But now these are popping up quite a lot.
Good. I know you, just as an engineer, are excited about doing those kinds of tests. I can't imagine how excited your students get about the prospect of being involved in an actual flight test. It must be quite exciting for them. Erica, we talk a lot about dual use of technologies and tech transfer. What applications do you feel like the hypersonics research and your particular expertise on materials can move into other sectors, civilian, non-defense sectors, and add value? What are some things that you've worked on or you can see this expanding out to?
Yeah, so a lot of the materials challenges are how do we sustain this operation of mechanical reliability and heat transfer at these extreme conditions? These are extreme conditions. And so benefits to sustained research that achieve these benchmarks are going to impact a number of Department of Energy sector applications. Just for example, if we can generate the propulsion that we need in a system with materials that can operate at these higher temperatures to provide the propulsion needed, then that will impact automotive, aviation, other engine component systems that are commercial based. Heat transfer and thermal management in microelectronics is also another category where even the scale of the component is different, but a lot of the fundamentals and the physics are comparable. So other new technology will definitely come out, in my opinion, from the thermal management material aspect of it. But what I'm also interested in is how this is going to impact our efforts in materials development as a whole. One of the big issues, as they indicated from the government, is that materials are the lowest kind of like TRL ready component for achieving this system. So how do we make things is also, I think, going to be a huge achievement through this effort, not only through additive manufacturing, but other manufacturing of textiles, fibers, composites, and ceramics, because the system requires a long list of different material types.
Good, thank you, Erica. I got two questions for you, Jess. I'm going to pull a quick one from the audience. So one of our clever viewers notes that speed of sound varies with density and temperature. Of course, there's a big gradient. So when you talk about a Mach 20 in some boost glide upper atmosphere, that's reference to the local condition. Can you just clarify that?
Yeah, absolutely. There's no Mach 20 things happening at sea level. We don't have the technology to make things like that. So those very high Mach numbers are very high altitudes, and
gotcha.
Typically the lower Mach numbers are flying at lower altitudes. The numbers that Dean Hahn quoted, and I've been trying to answer some questions as I can, at least the ones I can answer quickly. The numbers that Dean Hahn quoted for miles per hour, those were all based on sea level conditions,
gotcha.
Which it's relevant, especially to people like the Navy who want to do things that come off aircraft carriers.
Absolutely. So thanks for that question, Mark. So Jesse, back to you again. We know that modeling and simulation can play a very key role in modern aero design. What additional factors in CFD have to be considered when we push that envelope to hypersonics? And what are we maybe doing with your colleagues at U of A?
Sure. Well, I'll start this off by saying that I'm an experimentalist by trade, and I work with some fantastic computational people here at U of A. We've had some new hires in this area as well. So I encourage you to review the website to see the fantastic work that they're doing. The real challenge in hypersonics, though, is it comes back to this idea of heating. So once things start to heat, and this becomes an issue in hypersonics, you have to consider the thermal loads and the mechanical loads. So if you're working about subsonic, transonic, even supersonic to a degree, it's really the mechanical loads that are more important. But once things get really hot, then you have to consider all that stuff coupled together. On top of that, you've got non-equilibrium flows. Depending on the Mach numbers, these can get more and more challenging. You have coupling with structures. So if you have an ablating structure that's giving off material into the flow field, that becomes another challenge. So as we go to these higher and higher Mach number conditions where heating is so critical, things do start to become even more coupled, which has additional challenges on how to do the simulations and ultimately the ground testing as well.
Excellent. Erica, when you've identified or you've invented new materials like you do for hypersonics applications, how do you go about testing that? You talked a little bit in your slide about the facilities, but take us a little more details. We think of an acetylene oxygen torch, for example, but you're at much greater and higher conditions than that. So tell us a little bit about how you do your testing.
Sure. So the perfect test would be to make a new material and then flight test it, because that's the only way to truly capture all of the extreme environment effects that the material will see. So because that doesn't, that's not readily available and takes a huge effort, what we do is we set up a number of ground-based test facilities that, in my opinion, kind of rank order what you're trying to learn from the material response. And so the reason I said our torch is kind of one of the most important tools for us is because it does deliver the heat load. So the enthalpy is 40 megajoules per kilogram, which is a lot of energy. And the flight and the flow velocity out of that nozzle is over 200 meters per second. So we are generating flow and enthalpy effects that are critical to how the material responds, right? So how much of that gas species is hitting the surface and at what enthalpy. So to compare this with what is the standard for kind of testing, our torch is an evaluative, it evaluates the material. It's not going to be the final test. It'll evaluate materials so we can develop them. But for example, an arc jet, which is a very large, massive facility that delivers that delivers enthalpy at a high load and high flow velocity, will be able to test larger materials and introduce new physics into the test that a small lab scale torch like ours will not be able to do. So looking at, for me, the approach for testing is, we use this screening tool to vary heat load, so we can vary the heat flux. So the enthalpy out of the torch delivers a heat flux on the surface of the sample that's over 800 watts per centimeter squared, and we can sustain that heat load for tens and tens of minutes. And that's because we need to develop kinetic-based models to evaluate how the material reacts at that given heat load for a sustained period of time. So because our challenges are materials driven by thermochemical reactions on the surface and by kinetics, because the material dynamically responds and changes over time, we needed to develop a tool that encompassed kind of all of those things that are important to the materials evaluation of the response.
Thank you, Erica. Several of our audience submitted questions talking about earlier hypersonic programs, vehicles such as the X-30, which was a program in the 80s. Jesse, I know, like many engineers, you're a student of history. You want to comment a little bit on similarities or differences in today's hypersonic concepts compared to something like the X-30 from 30 or so, 40 years ago?
Mm-hmm. Sure. Yeah, so you're referring to the X-30, the National Aerospace plane, which was conceived in the late 80s and I think ended its lifetime in around the early 90s, maybe 93. It was never flown, and the idea was it would be a single-stage orbit space plane that could also be, modified for commercial flights, say, very quick commercial flights. One number I saw was DC to Tokyo in 2 hours, something like that. So that plane was big. I had this question ahead of time, so I looked up some of the specs. I don't want anyone to think that I know these off the top of my head. It's 160 feet long and a 74-foot wingspan. So this is a pretty big plane. And I don't want to get too detailed here, but when you have those larger aircraft like that, you start to have turbulent flow on most parts of the aircraft. And a lot of the emphasis in research in those years was done on turbulent flows, specifically some of the work that I do in the interaction of boundary layers and shock waves. They were all turbulent interactions. Today, a lot of the things that are conceived and being built are much smaller, such that they will not necessarily have fully turbulent flow on the vehicle, if any turbulent flow on the vehicle. And that changes the physics, right? The smaller vehicles will have transitional flows. I saw a question in the chat about boundary layer transition. This is a huge area of study in hypersonics. Because for these smaller structures, the boundary layer could be laminar or transitional, at least over much of the acreage, and very little turbulence. So that's one of the biggest issues that we see that's different now and today versus what was happening, say, 30 years ago.
Excellent. Now, we've seen a few questions about students. So let me go back to students. The recruitment of top graduate students is really the lifeblood of what we do in the research labs. Now, can you comment, each of y'all go with Erica and then Jesse, about the attractiveness of hypersonics research to students? Is it helping your recruitment experience? You want to speak to that, Erica?
Yeah, so I've had a really exceptional group of graduate students, undergraduate students, postdocs that have been trained in our research labs and have been excited to learn materials and aero, right? They're a unique group of kids and young professionals that want to continue in this growth mindset of learning materials, but also learning about the aero side of what the material will see. And so I've had exceptional students who are looking for this type of unique challenge because they have an interest in materials and they have an interest in aero. And with our research programs that are funded to do applied hypersonics research, they really get that unique experience. And so we're very fortunate to have a strong group of faculty on campus where we can form these multidisciplinary teams and train students from different departments.
Excellent. Jesse, what's been your perspective of students interested in aero and mechanical, and how much of a draw this is to help you recruit those great kids?
All right. So, you know, one of the things that as an experimentalist, I have the advantage of is that I have some really, you know, hands-on, tangible things students can work on. And, you know, I often make the joke that if you can hold a wrench or a screwdriver, you can work in one of our wind tunnel labs. So we involve students all the way down to high school who come in the summers and can help out, because there's always something you can do in a hands-on experimental project. Of course, there's high-end stuff that takes years of training to be able to perform, but we can always have students at all levels involved in these projects. And that's really been key to sort of promoting interest, with showing that you can be involved in these types of activities, even early on in your career.
Outstanding, outstanding. Erica, you're a materials science engineer. You want to just say a word, especially maybe those students out there that might be listening, students of our alumni. Can you tell us a little bit about what that entails and how that prepared you for this particular research line that you're in?
Yes, so in material science engineering, it's fundamentally the application of math, physics, and chemistry. And we're applying that to a group of atoms from the periodic table. And from there, your imagination can take over. And so that, to me, speaks loudly to creative students who want to use the language of math, physics, science to learn about how to apply them. And so for me personally, it's been very exciting to be able to use my materials engineering background and apply it to a number of different disciplines, because the materials are everywhere. And if there were not materials, there wouldn't be, you know, things to engineer with. So it really goes hand in hand. And I'm really fortunate that I have the best job in the world, and I get to work with students and share with them how exciting it can be to have a career in materials and engineering.
Excellent. You know, I think we're going to wrap up now because we're right about at the end of our allotted time to 12:45. But I just want to speak to the audience and say thank you for joining us. You know, our goal of this again was to reach out to you and let you see the exciting things that we have. It's really an honor for me to participate in this and to put on the stage, you know, my outstanding colleagues like Erica and Jesse, who are really, you know, pushing the limits of research, but are also outstanding mentors to their students and embrace all the things that we have around our missions of teaching and research and service. So I want to thank everyone for coming. I'll let Erica and Jesse have the final word to say farewell, but thank you for coming. Erica?
Yeah, thank you for joining us, and we look forward to continuing this discussion with you at any time.
And Jesse?
Same here. Thanks for coming. And I want to say that, you know, Eric and I are representing a very large team of exceptional faculty in this area. So I appreciate you reaching out to us, and we can talk much more about these topics with our colleagues.
Excellent. Yep. Built on a longstanding history of excellence at this university in these areas. So I want to say thanks to the audience and have a great afternoon. Thanks for joining us. Erica, Jesse, thank you for taking time to do this.